All right, so in the last example, we looked at this matrix. We computed the algebraic multiplicity of its only eigenvalues and the geometric one, and we found that A was not diagonal because this was smaller than this, really, because it didn't have two different eigen, um, a two-dimensional eigenspace. All right, so here's what the generalization of this idea is. So from the work in previous section, we get the following result linking diagonalization to geometric multiplicity. Let A be an n by n matrix, then A is diagonalizable. We know that's the same thing as you have a basis of eigenvectors, and so you need the sum of the dimension of E lambda of A, so the sum of the algebraic multiplicity, geometric multiplicity, to be equal to n. All right, so to determine how a matrix can fail to be diagonalizable, we consider the difference between the geometric and the algebraic multiplicity. All right, the theorem here, theorem 3.3.5, the geometric multiplicity of an eigenvalue is always less or equal to its algebraic multiplicity. All right, so the algebraic multiplicity is bigger in some cases, it's equal to the geometric multiplicity in others, but it can never be less. All right, so we'll prove this. Let A be a square matrix and let lambda be an eigenvector, an eigenvalue of A. Assume that K is the geometric multiplicity of lambda. We need to show that x minus lambda K divides P of A. So that's the same thing as saying the algebraic multiplicity is bigger or equal to K. All right, so we're saying that this divides, but we're not saying that a higher power doesn't divide. All right, so we're going to take a basis for E lambda. All right, so let's say that's V1, Vk. All right, so we're going to start with these vectors, and then we're going to extend that basis to a full basis for Rn. So that one will start with V1 through Vk, and then we'll put other vectors, Vk plus 1 to Vn. All right, so I don't know anything about these, but so this is for Rn. All right, so I'm going to look at what the matrix of A looks like in this basis. So I'm going to look at TA in this basis. All right, so for this, I'm going to apply TA to V1, so I'm going to get AV1, and I want to write this in terms of my basis BRN, then AV2 in terms of my basis BRN, and so on up to AVK in terms of my basis BRN, and then the rest doesn't really matter. So this part will be a bit random. So let's look at what AV1 is. V1 is a base is part of a basis for E lambda A, and so that means V1 is an eigenvector, and so I get lambda V1. And so that vector that I need in my first column, well, I'm going to use one of these and none of those, and so I'm going to get lambda of these, 0, 0. AV2 is going to be lambda V2 And so that's going to give you 0 lambda 0 0. All right, and so on up to AVK. The other ones, I have no idea what's going to happen, and I don't really need to know. I'll get a lambda, and then everything afterwards will be 0. And so if I look at what TA of B is, that's going to give you lambda, lambda. Those are going to be my first K column. So 0, actually let me be a bit more precise. So I'll get lambda, 0, 0, 0, lambda, 0, up to the kth one. And then underneath, I'm just going to get 0. The rest I have no control over, so I don't know. Let's call this matrix C. That matrix is similar to A. In fact, it's a change of matrix away, so it's going to be P from S to B, P of S to B inverse. And so it's going to have the same characteristic polynomial as A. And so PA of X is equal to PC of X. But this one, I have a bunch of nice columns and then a mess. And so when I expand it, no, 0, 0, sorry, it's just so many zeros, zeros, zeros. All right, so when I expand it on the first column, on the second column, on the third column, on the fourth, I'm going to get L minus X K times, and then I'm going to get some determinant of some piece of whatever the bottom part here is. But that means that lambda minus X to the K does divide PA of X. And that's what we need to show. Good. So at this point, we have found that the algebraic multiplicity is bigger than the geometric one.